Okay, so we talked about the 8-dimensional supergravity multiplets, where we have not only a gravity multiplet, but also gauge multiplets. So we have the possibility of all kinds of different interesting gauge groups. And we're going to talk about two kinds of string compactifications. Last time we went through heterotic compactification, and today we're going to do F-theory in 8 dimensions, which is really the right place to start with F-theory. I'll just kind of flip through what we did last time. We talked about general compactifications, and so we could characterize the two kinds of compactifications that seem to give interesting n equals 1 supersymmetric 8-dimensional physics as either compactifying heterotic or type 1 on T2, or compactifying F-theory down, in quotes, from 12 dimensions down to K3, and we'll see what that means in a few minutes. Just corrected the numbers that were on there last time. If you compactify, you get you get a gravity multiplet plus a bunch of gauge fields, and generically the gauge group is broken down to U1 to the 20, but as we discussed, if you compactify on a torus, and you go into, we went through some general discussion of lattices, which are going to be important for almost all the things we're talking about in this series of lectures. We classified integral lattices, even lattices, unimodular lattices, which are particularly important, equal to their dual, and talked about the connection between lattices and simply laced Lie groups. As somebody pointed out, the non-simply laced Lie groups, the definition of the Cartan matrix doesn't provide you with a symmetric inner product, so you don't have a lattice in that case. We went through toroidal compactification, observed that at certain special radii or at certain special moduli of the toroidal compactification, you get enhanced gauge symmetries. And so in the heterotic string, the gauge symmetry is characterized, or the compactification is characterized by a lattice, gamma d16 plus d, where d is the number of dimensions we're compactifying. And so when we go down, for instance, by 2 dimensions on a T2, then the lattice we're compactifying on has 2 bosons in the left moving sector and 18 bosons in the right moving sector, so that the lattice is, since it has to be unimodular by modular invariance, it's going to be 2 copies of U, 2 copies of E8. And so that gives us a picture of the moduli space, which is this Narayan moduli space for this lattice. And as we discussed last time, the condition then on what kinds of gauge groups we can get is that we can get any kind of gauge group which you can get by embedding the lattice associated with that, the root lattice of that gauge group, into gamma 218 in such a way that the right moving momenta, L squared, go to 2 on the lattice for the additional generators which enhance the original U1 to the 20 up to some U1 squared times some rank 18 gauge group. So that's the generic result for what you can get in terms of a gauge group in 8 dimensions, and we also have a picture of the moduli space. Sorry? Yeah? So gamma 218, that's a lattice, and 218 is the signature of the lattice, which means that if we diagonalize it, we will have 2 positive eigenvalues and 18 negative eigenvalues. So it's just a matrix. I mean, if we think of it as a matrix, gamma PQ has signature P comma Q, where these are the pluses and those are the minuses. So a Euclidean positive definite lattice will be all in the P part. Negatives will be all on the right. I'm just using this convention because this is sort of standard for a lot of the lattices we're going to be using.
So the simplest case you just reported, like gamma 1, 1.
That's right. That's U. That's right. But if we diagonalize that, right, I mean, that's just one of the Pauli matrices, right? If we take 0, 1, 1, 0, if we were to diagonalize that, which would be in a basis which is not necessarily an integral basis for the lattice, but just to diagonalize it to get a sense of the signature, it's got 1 plus 1 eigenvalue, 1 minus 1 eigenvalue, right? 1 comma 1 is an eigenvalue of this with eigenvalue plus 1, and 1 comma minus 1 is an eigenvector with eigenvalue minus 1. So that's a signature 1 comma 1 lattice, whereas what we've got here is a signature 218, which has 2 U's. These are indefinite signature 1 comma 1 lattices. That's where we get our 2 on the left-hand side. And then our E8s, E8 is a Euclidean lattice, and I put a minus sign in front of it so that it's all negative, right? I mean, we just had E8 up on the slide a few minutes ago. We take that lattice, we take the negative of it. It's now a negative definite signature matrix associated with a negative definite lattice. So gamma 218, we have this general classification of unimodular lattices in an indefinite signature, which is they're always just a sum of a bunch of U's, enough to saturate the smaller of the two values in the signature, plus a bunch of E8s. That's the general form of a unimodular lattice with not indefinite signature. Right, so this is associated with the left-moving bosons, and the 18 are associated with the right-moving bosons. Because in the heterotic string, we have 16 extra bosons on one side.
Yeah, but the signatures come with the opposite sign.
Sorry?
The signatures come with opposite signs.
Yes, because in that basis, the inner product on the lattice looks like L squared minus LR squared. That's the inner product. Yeah.
Can you just remind me how the counting works? So E8 has an 8-dimensional group lattice.
Yes.
So then I see 16. And then
That's 16, and then this is 2, 2.
So what's U is?
So we have the signature is, we have U here, which is 1, 1. Another U. Sorry, 2 U's. Thinking of K3. That's 2, 2. And then we have E8, which is 0, 8, and 2 of those gives us 2, 18. All good? Great. Yes?
The moduli space here, I'm not sure I understand what that. Shouldn't SO218Z be modding out? So should we mod out by T12?
So this is a choice of basis in which to write this. This is basically a choice of how the lattice is embedded in a real 20-dimensional space. So it's a choice of basis. So we can choose this SO18 is basically like, in SO3 is the set of basis elements you could choose in a 3-dimensional space. If you're fixing the signature, it's SO218. But then if you can mod out by SO2 and SO18 because those leave the decomposition of the signature in the same form.
I was just asking, isn't this SO218Z, isn't that the T-dualities?
It is. So once you've done this modding out, there's still a discrete symmetry group. This symmetry group is the symmetry group which leaves the lattice invariant. But it might move one lattice element to another lattice element. So for instance, one way of drawing this lattice here is like this in the WP space. Right? W has to be integrally quantized. P has to be integrally quantized with an R and a 1 over R. And there's a symmetry of this lattice which exchanges this basis vector with this basis vector. Right? It's a symmetry which takes, for instance, W comma P goes to P comma W. That's a symmetry of the lattice. So we have to mod out by that because those are physically equivalent. So that in this simple case, this is the T-duality group which inverts the radius. So this is in general going to be the T-duality group of this more general compactification.
So both sides are modding. Okay.
Yeah, sorry, it's really just you mod out by this and then you mod out by this. For some reason, people write it this way in the literature. I'm not quite sure how that convention arose or whether there's deeper meaning to it.
Why do the model only come from the octile? Why do we mod out only by compact parts?
So those would just be a relabeling of the 18 right movers or the 2 left movers, which would leave the decomposition into left and right movers invariant. So you're allowed to mod out by that because those would be equivalent points in the moduli space. So we talked briefly about what you can actually embed here, but I won't review that. So let me move ahead and move into telling you a little bit about F-theory, which is this other approach to doing the 8-dimensional compactifications, which we'll see basically gives you the same answer because it's a dual formulation. So this will give us a fairly complete picture of what you can do in string theory in 8 dimensions. So F-theory was initiated a number of years back by Vafa, and there was a pair of papers by Morrison and Vafa which elaborated on the structure and defined it in a fairly clear way, and I'll more or less follow some of the basics of those papers. And then we'll go a little further a little later in the lectures. The basic idea of compactification on F-theory is that we want to think of this as a compactification of type 2b where we include 7 branes. And the one way to think about this is in terms of the axia dilaton. So remember that in the type 2b string theory, we have, in addition to the dilaton, we have another scalar field, the axion. And these guys fit together into a complex scalar which transforms under an SL2R transformation group, which is a symmetry of the classical type 2b theory. So classically, 2b has an SL2R symmetry group actually acting in the usual way on tau. Tau goes to A tau plus B over C tau plus D, where AD minus BC equals 1. And this SL2R symmetry transforms this pair of two-form fields, the B field and the Ramon-Ramon B field, transform as a doublet under this SL2R transformation. So that's a classical symmetry of the theory. But in the quantum theory, we quantize the branes, so the F string and the D string become quantized, and we can no longer do a continuous SL2R transformation because a discrete unit of string has to transform to a discrete unit of string. So in the quantum theory, the SL2R is broken to an SL2Z. So this is very much like the moduli space we had before, but maybe a simpler example. This is the standard moduli space for the torus. Tau, this parameter, we know that e to the minus phi has to be positive, so this lives in the upper half plane, m tau greater than 0. SL2Z then is going to transform this thing, transforming the upper half plane, and when we mod out the upper half plane by SL2Z, that gives us the moduli space for a 2 torus, where tau is like the complex parameter of the 2 torus, the modular parameter of the 2 torus. So this is good. So if we just have a 2b compactification with no branes or any complication, we would just choose a constant value for tau, meaning a constant value for the axia dilaton. But some of the branes, in particular the D7 brane, are charged under both the axion and the dilaton. In particular, the D7 brane is magnetically charged under the axion. So this is just the standard coupling of a brane to Ramon-Ramon fields. We know that a brane in general will couple to the p+1 form field because it has a p+1 dimensional space-time trajectory. We drew that picture last time, I think. So the 7 brane couples to an A8 form whose field strength is F9, and the dual of F9 is F1, which is the D of the dilaton. So this is magnetically coupled to the dilaton. So what that means is that if we take a little circle around a D7 brane, the dilaton undergoes a transformation by adding 1, which is one of the SL2Z transformations. So one of the basic SL2Z monodromies is realized by going around the D7 brane. Now, since we have this doublet of B and B tilde, we can define in general a PQ7 brane, which will generalize this monodromy to an arbitrary SL2Z monodromy. And so the idea of F-theory is to consider a compactification where we compactify on some manifold which contains a collection of these PQ7 branes organized in such a way that we can close the manifold in a sensible way, and we have a varying axiodilaton describing, in some sense, a geometric toroidal fibration over the space which we are compactifying on. So often this is thought of as a 12-dimensional theory compactified on an elliptically fibered space. There is no real 12-dimensional supergravity. As we said, we don't know of any kind of 12-dimensional supergravity which doesn't have fields of spin greater than 2. We don't have a theory we can dimensionally reduce, but we do have an understanding of how to construct this kind of dimensional reduction from 2b, and there are various dual formulations in terms of F-theory and other things, which allow us to have a fairly consistent way of understanding what we're doing here. Yes, question?
Doesn't M theory already demetrize tau?
If we do a duality to M theory, yes. But then you have to take a decompactification limit again. There's different ways of thinking about it. I'm going to think about it this way because I think this makes it a little bit clearer what we're doing in some of the geometry we're going to do to construct compactifications in 8 and 6 dimensions. But there's an equivalent formulation, as you say, in terms of M theory, which I'm not going to talk much about. Other questions? Yeah.
The original hallucinations of having the extra 2 dimensions in some theory with one signature. There's some string theory to it.
People have talked about that. I've never understood how to make that into something really well-defined. I don't have anything useful to say about that. Certainly it's something people talked about. I think there was more discussion of that in the early days of the subject. People have certainly talked about 2-time theories, although it's a little hard to make sense of those and exactly how to do that in the context of F theory. I'm not sure how to do anything really constructive with. I don't know of any statements you can make that use that kind of construction which tell you anything that seems to be useful in actually moving head on. There may be some beautiful story there, but I'm not aware of how to do it. It's a good question. Yeah. So in general then, F theory is going to be some compactification, in quotes, of a 12-dimensional space on an elliptically fibered Calabi-Yau. And usually people draw fibrations as in this fashion where you have the total space here, X, the fiber comes in from the left, and the base space is on the bottom. This picture just means a space X, which is a base space B with a copy of T2 over it at every point. And if the base space here has complex dimension D, and we do the compactification, this is just like 2B compactified on a 2D dimensional real space. So we get a 10 minus 2D dimensional space-time in our non-compact directions. So to understand what we can get out of F theory, we need to understand a little bit about elliptic vibrations. And we need to understand a little bit about the geometry of spaces which you can build as elliptic vibrations over some base space. And this is a well-studied mathematical subject, and 8 dimensions is a great dimension to start in because that's where the story is clearest and simplest. So in general, unless the space is a product space, unless the total space is the base space direct product T2 topologically, there are going to be places where the elliptic vibration degenerates. That doesn't mean that the total space necessarily degenerates, although often it will if we have an interesting symmetry. It just means that the vibration structure degenerates. Just like S2 is an S1 fiber over the interval, and the fiber becomes singular at the endpoints. S2 is a perfectly smooth space, but it's singular as a vibration. So Kodaira classified the singularities that you can encounter if you have an elliptic vibration over a 1 complex dimensional base space. And there's a very clean and clear classification in which the different kinds of singularities are classified by the ADE root lattices. And each of the ADE structures is then associated with a non-abelian gauge symmetry in the low energy theory. So the simplest example is if we just have n D7 branes, n identical D7 branes, we know from physics that if you bring, from some of the discussions we've had before, that if you bring those together, we get an enhancement of the gauge group to a UN gauge group, which in the non-abelian parts of that being an SUN gauge group, which is the part we're keeping track of here with this ADE classification. In the Kodaira classification, that's realized by an AN-1 singularity in the elliptic vibration. So geometrically, there's this Dinkin diagram, and this has a very geometrical meaning. This represents a bunch of 2 cycles in the total space, which are being shrunk down together in such a way that the edges between these guys represent intersection points between the 2 cycles. So the Cartan matrix really represents the intersection form on the various 2 cycles which are being shrunk in the total space to give us this elliptic vibration. And again, in this M-theory dual you mentioned, one way to think about this fact that you get massless fields is that you can think of this as M2 branes wrapped on these cycles which become massless. But I'm going to focus on the 2B language where we just have D7 branes coming together, getting an enhanced gauge symmetry. But the beauty of this structure is that because it is essentially non-perturbative, because tau can range across the full moduli space, we're not stuck at small coupling, we can have complicated vibration structures where branes can come together and form groups besides SUN. We can get all of the simply laced Lie groups by bringing together the branes in different ways. So that's what we want to understand a little bit better to see what we can get out of F theory. So are there any questions so far about this picture?
So AN minus 1 singularity, just once again?
Yeah, you always subtract 1 for the, it's just the convention that, for instance, this is SU3, which is A2, right? There's 2 of these guys. It's the rank of the non-abelian gauge group is the number of, the number of roots is the rank. Here. Other questions? Yes, please.
Can you say a little more about what 2 cycles these are that are shrinking? Are these twos?
No, okay, so there's a total space which is T2 fibered over some base. So that's a complex surface in general. So it's a 2 complex dimensional space. And that can have various different kinds of 2 cycles other than just the fiber. It can have all kinds of 2 cycles living in it depending on how complicated the vibration structure is. And what's happening when you shrink these 2 cycles is some 2 cycle in that total space is compressing. So I'll actually do an example in just a minute of K3, and we'll talk about what the 2 cycles are. So if what I just said is not totally satisfying, we'll do an example in just a minute, and you'll actually see what the 2 cycles can be. We'll be a little more explicit about that. The cycles correspond to the nodes. The lines in between correspond to intersections, non-trivial intersections between those 2 cycles. So the A, if this is an SU3, then we would have 2 spheres shrinking, and their intersection number would be -1. That's how you get an SU3 gauge symmetry, is by getting these guys shrinking. Basically, these guys shrinking down correspond to the additional gauge bosons that you're picking up. Okay. Other questions? Okay, so let's do this a little bit more explicitly and get into an example. So the idea is we're going to compactify type 2b on a 2-dimensional space with a bunch of 7 branes. And how can we do that? So if we take a single D7 brane, it's a codimension 2 object. So if we look at a black brane solution, if the codimension is higher than 2, then you get some, just like electromagnetism, you get some effect which drops off as a power of R. If you have a singular or a black brane in codimension 2, you get a deficit angle at infinity. So you can see the presence of that thing all the way out to infinity in a deficit angle, meaning that if I go out to radius r, the circle is not circumference 2 pi r, but it's 2 pi r minus 1/6 pi r. So there's a deficit angle of pi over 6 associated with each one of these D7 branes. So that we can think of as a little bit of discrete positive curvature in our 2 real dimensional space. So we have to patch together pieces of deficit angle corresponding to positive curvature to get some compact space. And there's only one way to do that. If we had negative curvature, we could get all kinds of homogeneous surfaces. But with positive curvature, all we can do is form a 2-sphere. And since we need total curvature 4 pi, we need precisely 24 of these guys. So to build an F-theory or a type 2b compactification with a bunch of 7 branes, we need to have 24 of the 7 branes, 24 points on the 2-sphere. And each one is going to be associated with some 7 brane. Now, they don't all have to be D7 branes. They can have different monodromies. In fact, if they're all D7 branes, you're going to have trouble because you might not have the right monodromy. If you go around all of these guys, let's say there's 24 things here, each with an SL2Z monodromy. If you go around all of them, you get the product of their monodromies. And that has to wrap around the other side of the sphere and compress to the identity. So the product of the monodromies has to be equal to 1. So to build a compactification, we need a choice of 24 consistent points on the sphere with PQ7 branes in such a way that the product of the monodromies is 1 and the total curvature is 4 pi. So geometrically, we can think of what's happening as the sphere having some sort of positive curvature. And we know that for a supersymmetric compactification, we need a space, a Calabi-Yau space, which is going to have total Ricci curvature vanishing. So these singularities are basically ways of sort of kicking in a little negative curvature to balance that out. So when we do this on S2, we get an elliptic vibration with 24 singularities over S2, which is the same as P1. This surface is known as the K3 surface. The supersymmetry condition on the geometry basically says that the total space of this thing has to be Ricci flat. Therefore, the whole thing is going to be a Calabi-Yau, and there's only one Calabi-Yau, it's K3. And in fact, this is a standard way of thinking about K3 is as an elliptic vibration over P1 with 24 singular points. Okay? By supersymmetry. So one way to argue more strongly for that is to go into a dual picture like the M-theory picture where you have a geometric compactification. Another way to argue it is that if we have this configuration of these guys, this is the combinatorial data which you need to specify K3. So if you prefer, I can read it off from the combinatorial data that this is the combinatorial data needed to describe a K3 surface. This is an elliptic vibration of a K3 surface. So let me just tell you a little bit more about K3, because we're going to see this in a number of different contexts. So it's useful to have several ways of thinking about K3. Somebody asked a minute ago, what are the cycles which are shrinking? So K3, I'll tell you about K3 in bits and pieces through these lectures, but let me tell you right now about the two cycles in K3. K3 is a complex surface, so it's 4 real dimensional, and there are a bunch of two cycles in it. There are 22 two cycles, and we can write down the intersection form of those two cycles. In other words, if we have a two cycle, here's K3. We have a two cycle, we have another two cycle. There's going to be some intersection between those. And so we can write down a 22 by 22 matrix, which is the intersection form. And by Poincare duality on surfaces, this thing has to be a unimodular lattice. And it is, in fact, the unimodular lattice gamma 319. So there are 22 linearly independent two cycles, and they live on the lattice gamma 319. So you can start to see how it's going to connect with what we did in the heterotic. It's often helpful, and we'll actually use this a little later, to think of K3 not in the language of a toroidal vibration over P1, but rather in an orbifold language. So there's another way to construct a limit of K3, which is the orbifold limit. If we take T4 and we mod out by the orbifold action Z2, so we take two complex variables, Z1 and Z2, take Z1 to minus Z1, Z2 to minus Z2. This is an orbifold. It has 16 fixed points, right? Clearly, if we take Z1 goes to minus Z1, 0 goes to itself. Notice also that this point here, which goes under Z, goes to minus Z down to here, is equivalent under a lattice shift to that middle point. Similarly, this goes to here, equivalent to that. This goes down to there, equivalent to that. So on each of the two tori, thinking of T4 as a product of two tori, in each of these there are 4 fixed points. 4 times 4 is 16. So there are 16 Z2 singularities. So those are singular points in this K3. So this is a singular limit of K3. To get back a smooth K3, we have to take those orbifold points and blow them up, which means replacing them with a P1. Basically, you replace the point with all the possible lines going through that point, giving you a full P1 of extra points plugged in there. That turns in, that's a standard procedure in algebraic geometry, which takes a space with an orbifold singularity and smooths it and gives you a smooth surface. So in this case, if we blow these things up, we get 16 cycles, which I'll call EI, which are P1s. And so from here, we can pretty much see why this is the right intersection form and homology group for K3. From the torus, T4, there are 6 two cycles on T4. We can choose any pair of 2 distinct directions, and we get a 2 cycle, right? There's 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, etc. And these guys intersect in pairs to give us intersection forms that look like U, right? 1, 3, 1, 2, which is a cycle given by the 1 times the 2 cycle, intersected with 3, 4 intersects in a point, but 1, 2 intersecting with 1, 3, since the 1s here can be parallel, they don't have to intersect, does not have to have an intersection. So the T4 gives us essentially 3 copies of U, and then these EIs, of which there are 16, are sort of bulk cycles, and each one is a P2, which has an inner product with itself of 2. So this gives us a set of 16 cycles plus 6 cycles, which are 22, which roughly speaking give us the right structure here. This is a little bit glib because this actually, the things I just told you about only generate a sublattice called the Kummer sublattice of the full H2 lattice. To complete the H2 lattice, you have to include some fractional combinations. Because this is an orbifold, there are various fractions of branes which are allowed to be included, which give you the full K3. But this hopefully gives you a little bit of a feeling of how K3 has, in one sense, a limit as an orbifold here, and in the other sense, we can think of it as an elliptic vibration over P1. Any questions about that? So this basic idea that we have to have 24 of these guys, 24 of these singular points to build up a total space which is a K3 is going to come back in a more complicated way when we go down to compactifications to lower dimension. And there's a similar story. The Kodaira story is amplified a little bit, and we need to do more and more complicated things as we go down in dimension. So I want to make sure we're clear on what's going on here, because this is basically the key to doing it in all the lower dimensions as well. Any questions about any of that?
So in the case of the Zoom K3,
Yes.
the radius of the P1 doesn't matter. We get
Well, that's one of the moduli. So there's a bunch of moduli of this K3, and one of the moduli, for a given cycle, one of the moduli is going to be the size of that P1 essentially.
that's what we move out.
Right. So in the orbifold limit, we've moved to the edge of moduli space where we hit a singular version of the K3, and then there's a whole bulk moduli space in which everything is smooth and all the P1s are finite dimension, finite size.
Any finite size is possible.
Well, there's a moduli space, and since it's only, I mean, there's a relationship between all these things. In particular, for similar reasons, there's actually a restriction on where you can place these 24 singularities. There's not 24 complex degrees of freedom, right? Because we only have 22 mod sum symmetry moduli to play with, so we can't independently dial the positions of those 24 singularities. We can dial maybe 19 or something of them, and then the other ones are going to be fixed. So let's dig in a little bit more to how to think about this. So we want to have an elliptic vibration over P1, by which we mean that there's a complex torus everywhere on the sphere, and at certain places that complex torus becomes singular. Yes?
So can I just maybe ask in a little more pedestrian language?
Yes.
So what you're saying, I think, is these D7 branes magnetically source C0?
Yes, exactly.
Because it's magnetically sourced, there's some Dirac string or something? Some equivalent of that?
No, they produce a monodromy.
Well, I think is that the same thing?
Well, the Dirac string would be if you had, the Dirac string is a sort of an artificial thing which is good, sorry. It's like a Dirac string. It's like a Dirac sheet in this case. It's like, yeah, I'm sorry, that's right. You can think of this as like a Dirac sheet stretching from the D7 brane out to infinity. And when you pass the Dirac sheet, C0 or chi undergoes a transformation by chi goes to chi plus 1. That's right, I'm sorry, I was...
And then the statement that all the monodromies have to be one is some statement about how you need to some point.
Right, when you go all the way around all of those guys, since this is a compact space, you have to be able to go around to the other side of the sphere.
So it's like you need to have a net charge 0.
It's just like having to have a net charge 0, exactly right. Because at the end, the total monodromy around all these things is the same as the monodromy around some smooth point on the other side, and that has to be a trivial monodromy. That's exactly right. Yeah, good, thanks.
One more question. So,
Yes.
So the T4 mod Z2, the examples I've seen, it's usually like C2 mod some discrete group. Is that just because I'm looking locally, or is it some different limit? Or?
Well, sorry. If you look locally at C2 mod Z2, this is the compact formulation of the K3. So if you do C2 mod Z2, you're going to get something which looks like one of these 16 orbifold points. And then often people will go through an explicit blow-up of that space. I'm not going to go through that now. But that's a local description of the physics here. So there's 16 copies of that going on here in this orbifold K3. That's right. Yes?
Is it possible to identify the T2 on the base with any of the T2s in the bottom picture?
Good question. I've actually thought about this, and let me see if I can remember whether I thought anything useful when I thought about this. I would waste cycles if I tried to. I think there's something useful to be said there, but it's not in my mind at this time. So pester me after, ask me after, after the lecture, and I'll be happy to talk more with you about that. Okay? Good. Other questions? Yes, please.
So you said there were 22 cycles. Did you mean 22 non-contractible cycles? Or
22 non-contractible cycles. The dimension of the second homology group is 22-dimensional. So there are 22 topologically independent non-contractible cycles in a smooth K3.
Okay. Can you say anything about the homotopy group?
The first homotopy group vanishes, and the second homotopy group is, I guess, closely related to H2, if not the same as. Okay. Okay, so one way of thinking about what's going on here is to write down what's called a Weierstrass form, which is an explicit algebraic expression characterizing this elliptic vibration. So first of all, let's start with the statement that we can define a torus by a cubic equation in P231. I mentioned the other day that we could define a Calabi-Yau general dimension by a hypersurface of degree p plus 1 and CPP. This is another way of getting a torus. If we just take the equation y squared plus x cubed plus fx plus g, and I stuck some z's in here to make it a hypersurface in P231, this thing is going to define a torus, where f and g characterize the modular parameters of the torus. So you could, for instance, write the j function of the torus in terms of f and g. The way we want to construct the elliptic vibration, and I'm actually not going to use the Weierstrass form very much at all in the discussions of F-theory. I just want to give you, because it's used a lot in the F-theory literature, I want to give you a sense of how it works, and because it gives you a slightly more hands-on sense of what's going on in these compactifications. This is the Weierstrass form for a elliptic curve, or a torus, and so what we want, basically, is to have a function. We have our base. We want to have a function, f of w and g of w, two functions, f of w and g of w, so that the elliptic curve at each point is characterized by f of w and g of w at that point. Now, let me just point out that this torus is going to be singular when this equation is satisfied. That's easy to, let's just quickly derive that, so I don't seem to be pulling too many things out of a hat. If we have an equation for a hypersurface p equals 0, in this case p is a function of x and y, the condition that it's singular would mean that dy of p equals d dx of p equals 0, right? There's no tangent space to the thing at that point. And we can just check that here. d dy gives us 2y, which has to equal 0. That tells us that x cubed plus fx plus g equals 0. And d dx goes to 0 implies that 3x squared plus f equals 0, right? So we have those two equations. And that means that f equals minus 3x squared, right? So if we plug that in here, this is now minus 3x cubed. So that means that g is equal to 2x cubed, right? And if we take this thing and we take 27g cubed, that's equal to, 27g squared, that's equal to 4 times 27 times x to the 6th. And if we take, try to sneak it in here, 4f cubed, that's equal to minus 27 times 4 times x to the 6th. So if we add those two things up, we get 0. So therefore, this thing is singular precisely when that equation vanishes. Right?
And you've dropped the z condition because you scaled away z?
Yeah, I threw in the Z here just to make it clear that we could do this in as a hypersurface in complex projective space that compactifies the whole thing. I threw it away because here I'm not worrying about the point at Z equals infinity. Z equals 0, I guess. Sorry, I'm not worrying about, there's some point in this complex projective space that I'm not worrying about.
So you're just going to a patch.
I'm just going to a patch, exactly. Yep. Okay, so now what we want to do is understand this more globally. We have this base space. F and G are going to be functions on the base space. And near a singular point, we're going to have this equation where F and G are functions on the base characterizing which elliptic curve we have. And at the singular point, W equals 0, this equation is going to be satisfied where that elliptic curve, that torus, becomes singular. So we're going to characterize the singularities of this torus vibration over the base in terms of the behavior of F and G and delta, the discriminant locus, near W equals 0. So basically, what Kodaira showed is that if we know the vanishing order of F and G and delta at a point where we have a singular fiber because the discriminant vanishes, then we can characterize the type of singularity that we have. So the simplest kind of singularity, which we've been talking about a couple times, is the AN-1 singularity. That happens when F and G are fine, they're smooth, they're just non-zero complex values. And delta, once you write down this discriminant, disappears up to some order W to the n. So when delta vanishes to W to the n, it's like bringing together a bunch of singularities to one point. So this then becomes W to the n. And we get an enhanced singularity, which is associated with an enhanced gauge group. In this case, we know what the gauge group is. It's an SUN gauge group because this corresponds to bringing n d7s together. I'm just keeping track of the non-abelian part. I'm actually kind of eliding discussion of U1s. There's a bunch of issues about U1s, which sometimes in the low energy theory become anomalous, and then there's a sort of Stuckelberg mechanisms with lifts, some of them. It's a little more complicated if you want to keep track of the U1s. And so just to simplify the discussion, I'm not even going to try to keep track of the U1s. In particular, Kodaira's classification is the classification of non-abelian gauge groups.
Another comment is that this is the first paper on FTH today.
What's that?
This is related to the first paper on FTH.
Oh, really? Oh, good. I haven't looked at the archive yet. It deals with those U1s? Good. Okay, cool. So Kodaira basically produced this nice table, which is the key to F theory, which tells you, or it's the key at least from the point of view of the Weierstrass equations, it tells you, if you know what the vanishing order of F and G and delta is, it tells you what kind of singularity you have, and therefore what kind of gauge group you have. And so as I mentioned, the marvelous thing about F theory is that you can get not just the classical groups, SUN and SON, but you can get, for instance, E6, E7, and E8 by putting enough orders of vanishing into F and G. You're bringing together these branes in a complex way, which produces these complicated sorts of singularities. So this is actually related to something that Oliver and Barton Svebak and collaborators looked at years ago, where they looked at the way that gauge symmetries like this appear as you bring together branes in different ways. But in F theory, it comes together to give us a mechanism for compactifying a theory and getting all kinds of different gauge groups out. If the order of vanishing gets to be too big, you cannot resolve this to a Calabi-Yau by just blowing up the fibers. You have to do something more dramatic, like perhaps blow up the base first and then blow up the singularities in the fibers. So these are the things where you can get a Calabi-Yau by blowing up these cycles, which are shrunk to points. Okay. So let me just go through a classic example. This is one of the first examples that Morrison and Vafa went through, just to give you a sense of how you can get the more unusual gauge groups in a fairly clean way in this theory. As I say, I'm not going to talk too much about Weierstrass forms, but I'll give you the Weierstrass form for this. And part of the motivation of the original work on F theory was to try to understand, or part of what they were trying to do, was to understand the duality between heterotic and F theory, which they worked in 8 dimensions to begin with, and then in lower dimensions. So one thing we might want to look at is a typical heterotic compactification, say heterotic on a torus with no Wilson lines, which has 2 complex moduli, basically the complex modular parameter of the torus and the volume plus the I times the B field on the torus give us 2 complex parameters. And we expect a gauge group of E8 cross E8, because if we don't turn on Wilson lines, we'll leave the whole gauge group unbroken. So how do we do that? Well, we want to construct an elliptic vibration over S2. The total degree of the discriminant locus has to be 24, right? We decided we had to have 24 singular points. Therefore, delta has to be a polynomial of order 24 in the coordinate on the S2. So if delta is a polynomial of order 24, then f has to be a polynomial of order 8, because you cube it, you have to get a 24, and g has to be a polynomial of order 12. So we need to write down a polynomial of order 8, which has 2 E8 singularities. One let's put at z equals 0, and one let's put at z equals infinity. For an E8 singularity, we need the order of vanishing of f to be at least 4, and the order of vanishing of g to be at least 5, and delta, the discriminant locus, has to vanish to order 10. So Morrison and Vaffer wrote down the answer, and we can almost just read it off of these conditions. F around z equals 0 has to vanish out to order z to the 4th, but around z equals infinity, this 8th order polynomial has to vanish out to order 1 over z to the 4th, and therefore it's really just going to be a parameter times z to the 4th. Similarly, g has to have its first non-vanishing term at order 5 around 0, and at order 7 around 12, and therefore it can only have 3 possible terms, and we can use residual degrees of freedom, like the scaling freedom of the variable z, to get rid of some of these degrees of freedom, leaving us with 2 modular parameters, alpha and beta, corresponding to the 2 complex moduli of the theory here. If we plug in f and g into the discriminant locus, you see that we get f cubed is z to the 12th, g squared is z to the 10th, and therefore there's going to be a minus 27 z to the 10th. Sorry, that should be plus 27. I changed conventions at one point. It should be a plus 27 z to the 10th in the discriminant locus. This is precisely what we asked for. So the Weierstrass form for the E8 cross E8 theory in F theory is this guy right here. Any questions? Delta needs to be of order 24 because we want 24 singular points. That's what we needed in order to close up the singularities into a sphere. So each of the singularities, each of the contributions to delta represents one D7 brane. So the order of vanishing of delta represents the number of D7 branes, essentially, the D7 brane charge, or really the deficit angle associated with that singularity.
So at a generic point in the modular space, when the singularities are separated, the vanishing order of delta is 1 at each singularity.
Correct.
And then you
That's exactly right. Exactly right. At a generic point in moduli space, you have 24 points, all separated from each other. Each has a deficit angle pi over 6, and there's no non-abelian gauge symmetry. This is the generic point in moduli space corresponding to the compactification of the heterotic string, where we turn on arbitrary Wilson lines and break the gauge symmetry down to U1 to the 18 times U12 from the gravity part.
So if there are, so at this in this picture,
Yes.
at each point the order of vanishing of delta is 10.
Correct. Good point. So there are 4 extra singularities floating around here. We have not completely. Once we do this, we can use these parameters to which will control where those other moduli are. But you're absolutely right. There are 4 further isolated singularities here. Well, one thing they mean is that you could bring at least one more in to build a bigger enhanced gauge group. Because this is not the biggest gauge group you can get. Remember, we discovered from the heterotic point of view, when you compactify on T2, you can get enhanced gauge groups whose non-abelian structure has rank greater than 16. And that way that happens here is by bringing extra D branes into here. Now, you can't necessarily build something bigger than an E8 because you might make a singularity that was too big. But you can break these apart and move them together in different ways, which might enhance the symmetry. Exactly. That's exactly where I'm going from there. So yeah, I didn't mean to imply that you could add things to the E8. You can't add things to the E8. I think Oliver and Barton and people showed that there were some problems with that. And it wouldn't make sense because it would give you a non-Kodaira type singularity if you added something to the E8. But you can do other things like break the E8s apart and add them to other things.
So didn't you show that the highest group that you got yesterday was SU19?
Yeah, so how do we get that? So let's look at that. So let's try to get the global picture of what we can get from the F-theory point of view. So I'm going to be a little heuristic here, but you can sort of see how this works out. Remember what the structure of H2 of K3Z is. It's gamma 319, right? So that's the full space we have here is a K3. But we're insisting that we have an elliptic vibration. That means that we've chosen two cycles. One of them is the fiber cycle, that's a cycle. And the other one is the section, which is a point in the elliptic curve for every point in the base. That gives us two cycles whose intersection number is 1, right? Because the fiber and the section intersect in 1 point. And therefore, that essentially gives us a piece which is a U, which we have to take off, because we can't shrink those guys. We can't shrink everywhere the fiber or the section. So that essentially gives us gamma 218. In that gamma 218, we are allowed to shrink any cycle whose inner product with itself is negative, which actually means it's -2, because there's a nice little formula from algebraic geometry called the Junction Formula, which says that K dotted into a divisor plus, or dotted into a cycle plus cycle dotted itself is the Euler character, which is 2G minus 2, where this is the I haven't told you what K is yet. We'll talk more about the canonical class when we get to the 6-dimensional theory, but basically this vanishes because it's a Calabi-Yau manifold. This is like the fact that the first Chern class vanishes. So basically, the inner product of the cycle with itself, the cycle squared, is 2G minus 2, and the cycles which you're allowed to shrink are spheres, genus 0. So when xi dot xi equals -2, we're allowed to shrink those cycles. And so we're allowed to shrink negative definite 2 cycles in this gamma 218, and those give us new non-abelian gauge bosons, essentially reproducing this picture that the possible gauge groups we can get are those whose negative root lattice embeds into gamma 218. So there's a little bit of math here, which I'm not sure I could do justice to, but the story is, and this is essentially what Morrison and collaborators worked out in some papers, that this embedding here, well, they were at least working out the duality between the heterotic string, focusing more in those papers and in the original F-theory papers on the moduli space, that the moduli space of the heterotic string is basically the same as the moduli space of compactifications on elliptic vibrations. So the upshot is, because these two theories give essentially the same physics, the same moduli space, the same possible gauge groups, these are dual descriptions of the same physics. So this kind of concludes the picture in 8 dimensions. We showed that there's no strong constraints on what group you can get, but in the two pictures we understand, to get 8-dimensional string compactifications, we are constrained to gauge groups whose lattice fits into gamma 218, and we have a moduli space of that form. So I would say the challenge in 8 dimensions, this is all sort of understood, the challenge in 8 dimensions is to see whether one can make any sense of any of these other things here. It seems hard to imagine that there are going to be additional string constructions, but one might be clever and come up with some. The other alternative would be to see whether there's some way to rule out or show that there are inconsistencies with some of those other theories. So that's kind of the story I wanted to tell you in 8 dimensions. I'm happy to stop for a bit and take questions, and then I'll start a little bit into 6D. Since, yeah.
Your statement on the heterotic side was the highest rank you could get was 18?
Correct. Same thing here.
So,
because we can only shrink negative definite cycles, and therefore, at most, we can get a lattice of dimension 18, which is negative definite signature. So in F theory as well. So for instance, I mentioned that there's a realization of SU18, which is rank 17 but not 18, by Gannour and Morrison and Seiberg, which they did with an explicit F theory compactification.
So I'm not seeing it from the lattice point of view, but just from the point of view of the singularity
Yes.
So if two of them are going to enhance it to rank 18, are the other two left over for the B and C Bernoulli manifold, or?
No, it's just that you don't have enough degrees of freedom to pack everything together. You know, you'd like to be able to build it up to SU25 by putting all 24 singularities together, but you can't do that. First of all, the monodromies are not right to make them all the same brane. But basically, once you get up to 18 or 19, I mean, it gets very hard, actually, once you get up to 18 or so to pack more, or once you get up to 16, it gets hard to pack more things together. And so they, found this nice F-theory compactification, which gives you SU18, and there should be one which gives you SU19, although I believe it's never been written down. Yes? Well, because in F-theory, we need to choose an elliptic vibration. And that means we've kind of taken away the fiber, which is a cycle here, and the base, which is another cycle here. And so this is, again, a little bit heuristic. We're taking away two cycles whose intersection is 1. That essentially strips off a 1-1 from the lattice. Other questions? Yeah.
What's the largest dimension in which a negative CC is consistent with SUSY?
What's the largest dimension with negative, where you can have an ADS compactification?
Or I guess a related question. Are these AP vacua are all Minkowski?
These are all Minkowski. I don't offhand know what the answer. I'm sure somebody in the audience knows the answer to that. I'm not coming up with it offhand. What is the highest dimension where you can come up with a negative?
Well, 7.
Well, you can certainly do it. Yeah,
you can do ADS 7 cross S4. So.
Right. I don't think you can. I don't think you can do it in 8. You can definitely do it in 6, and as you point out, you can definitely do it in 7. I don't know of any way of doing it in 8, but I'm not sure that there's not some. I'm focusing here on Minkowski vacua. I would hesitate to go out and say that you can't get an 8-dimensional one, but I don't know offhand of any way of doing it. So probably a 7 with ADS 7 cross S4 is the best known, unless somebody else has a counterexample. Okay, so that's the story in 8D. Sorry, another question.
So you've shown that the heterotic and F-theory pictures gave the same low energy physics?
Yes.
Is there more that has to be done to argue that this is a duality of the string theory?
Yeah, good. So in everything I'm saying here, I've been really focusing on just very rudimentary discrete data, like the set of multiplets and the gauge group, and I'll talk about the matter content in 6D. You can write down two theories that look the same at low energies, and there might be completions of those which have different characteristics. And I've not touched on that at all. Even in 10D, when I made the assertion that, okay, we know what the different theories are, and we can pretty much rule out everything which isn't realized in string theory, somebody pointed out, well, what if there are higher derivative corrections? Right? There could be different completions involving higher derivative corrections. It's an excellent project to try to understand whether those are also constrained. No one has a proof, because nobody has a complete definition of either of these theories. Nobody has a proof that they're equivalent. But all the evidence shows you can match up all kinds of things, including the moduli spaces, enhanced symmetries, BBS states and things. All of these things match up very nicely and indicate that you should have the same thing. Oliver?
I was just going to make a comment on the previous question. So there was a classification of superconformal quantum field theories, and the highest dimension of which there was one was 6. So, and then superconformal quantum field theories have the same symmetry group as supersymmetric ADS spaces have.
Good. So that would.
Group. So I think that
would fit in with the 7-dimensional maximum dimension. Good. So that all seems to fit nicely together. So unless somebody says something different, we can maybe.
Is there some type, some sort of way of seeing that you can't have a CFD above that? Is there some sort of consistency condition on the, or is it just that it isn't enough?
I'm going to punt you guys to.
So I believe there was a proof, but I have no idea how the proof worked offhand. I mean, it was about the algebraic structure.
Okay. I'm going to take the sorry, one more question.
Yeah, one more question. So this is the lattice way of doing this is sort of a direct heterotic F-theory duality. Is there a way of seeing the lattice from the point of view of heterotic to M and M to F? Or do you sort of express that?
I think you would see the same sort of thing in M theory, because you have also compactification on K3 and in the M theory side. So you would have similar cycle shrinking. It could be similar. Let me get a little started on 6 dimensions, because I've got a lot to say about 6 dimensions, and I want to, at the end, have time to say a little bit about 4 dimensions, too. So let me spend maybe 5 minutes today kind of warming up on 6 dimensions. So each time we go down by a complex dimension, a pair of dimensions, life gets much more complicated. Now we have a nice picture of how heterotic and F-theory work, and now we want to talk about supergravity in 6 dimensions. So in 6 dimensions, we have the additional exciting feature that we now have matter. Right? We haven't really had matter up to this point. We've had gauge groups, but now we have a matter multiplet. So we have a supergravity multiplet, a vector multiplet, hypermultiplets, which include scalar fields, transforming in some general representation of the gauge group. And we also have a tensor multiplet, which includes a self-dual 2-form. Remember, in 6 dimensions, a 2-form potential can be self-dual or anti-self-dual because its field strength is a 3-form, and 3 plus 3 is 6. So with a 3-form field strength can be self-dual or anti-self-dual. So we have different Poincare representations, different Lorentz representations for the self-dual and anti-self-dual, and they fit into different supersymmetry multiplets. So we have to keep track in 6 dimensions of 3 kinds of multiplets. The tensors, of which there are some number t, the vector multiplets, of which there are some number v, which I will describe in terms of a gauge group, which I'll write as a semi-simple group G, which is the product of G sub k, again, eliding complications due to U1 factors. And then there's matter, which lives in some representation of G. There's an interesting symmetry of the theory, which is an SO1T symmetry, under which the B fields transform. So there's one of these guys and T of these, and there's an SO1T structure under which these guys transform, and in particular, the scalar fields here, the phi's, live in a moduli space which is SO1T mod SOT. So these guys will play a role as important parameters, as a set of moduli which are going to come in various ways. In some compactifications, they're going to be basically the Kähler moduli of the compactification. But from the point of view of supergravity, these are the scalar fields in the tensor multiplets. And they play an important role in determining things like gauge kinetic terms and things like that. So here's the plan. I'm going to start by talking about constraints on the space of theories. So in 8 dimensions, we didn't have much to say about this space script G because there were very few constraints that we could write down. In 6 dimensions, because it's once again a dimension of the form 4k plus 2, we have very powerful anomaly constraints. And those will allow us to strongly constrain the set of possible supergravity theories. Then I'll talk about 3 kinds of constructions in sort of increasing order of complexity, all of which have some relationship to one another, and all of which are kind of related to the lattice structure that we've been kind of going along with through these notes. I'll start with intersecting brane models in 6 dimensions. It ties in nicely to some of the things Miriam has been talking about to give us some simple examples of intersecting brane models. I'll then talk about what happens with heterotic when we go down to 6 dimensions. We get an additional complication, which is that we can now have instantons. Remember, we couldn't turn on gauge field strength F in a 2-dimensional compactification because it broke supersymmetry. Compactify in 4 dimensions, we get instantons, which makes this story more complicated. I'm going to look at a simple class of these compactifications, which involve essentially U1 type instantons, which are essentially what are called magnetized brane models, which are morally, if not actually, related to, through T-duality, to the intersecting brane models, and have a nice characterization again in terms of lattices and the K3 lattice. And then I'll talk about F-theory, where we have the additional complication that the base is now itself a complex surface, whose intersection form is itself a lattice. And in fact, we'll find that there's a close relationship between what we can see from the point of view of the low energy constraints and F-theory. So most of that I'm going to do tomorrow. Let me just tell you a little bit about what we can use to constrain things, and we'll continue tomorrow. There's a bunch of chiral fields in the 6D theory. There's not only the fermions, but also there are self-dual and anti-self-dual 2-form fields. Just like in 10 dimensions, we had the self-dual 4-form. So all these are going to contribute to anomalies. And in 8 dimensions, 6 dimensions, the anomalies are characterized by a p plus 2 is 8 form, given by square diagrams, where we have external legs which are r's or f's. So we get some anomaly of the form, some r to the fourth terms, some f to the fourth terms, some r squared, f squared terms. Once again, there's a Green-Schwarz mechanism. So now this is complicated by the fact that we have not just one B field, but we have T plus one B fields. We've got the anti-self-dual B field and T self-dual B fields. All of them can contribute to the anomaly cancellation. So this was worked out for T equals 1 by Green-Schwarz and West, and then generalized to general numbers of tensor multiplets by Stanyoti and Sadov. And I'm essentially going to follow their notation for the anomaly cancellation with some tweaks which make everything work out much more nicely. Let me give you the general form, show you how it simplifies at T equals 1, and then we'll stop for today. So today I'm just going to tell you what the anomaly conditions are, and tomorrow I'll tell you about what we can do about solving them. So this, let's just parse what this equation says. It says that the anomaly 8 form factorizes, but now it's not just a product. Remember, in 10 dimensions, we had the equation I12 equals Y4 X8 was the factorization. You just multiplied those two things together because there was one class of diagrams with one B field in the middle, which had some stuff out here and some stuff out here. Now, since we have T plus one of these things with this SO1T symmetry, we have an inner product on R1T, omega alpha beta, where alpha and beta are indices in this 1, T dimensional space. And the x's, we've now got an x4 and an x4, coming from 4 field strengths on each side, are given by a linear combination of things of the form trace r squared, multiplying a vector A alpha in this 1T space. And for each component of the gauge group, we have a trace f squared. There's a constant normalization factor which depends on the kind of gauge group, which I've stuck in here because it actually makes everything turn out very beautifully in the end, and I'll tell you more about that next time. So these are just constants for now. For SUN, it's going to be 1. For E8, it's 60, et cetera. And then there's a B, a vector B, for each component of the gauge group. So the A's and B's are vectors in R1T, and the total anomaly basically says if you take this vector and dot it into itself with omega alpha beta, then you're going to cancel the anomalies. So what I'll start off by talking about next time is the following, that if the number of tensor fields is less than 9, then the anomaly constraints, which I just described, constrain the set of possible theories so that there are only a finite set of possible gauge groups and matter representations which are possible, compatible with not only anomaly cancellation, but one other constraint. So let me tell you about that, and then we'll stop for today. The primary constraint we're going to use to constrain the set of possible theories is anomaly cancellation. And in case that seems a little abstract, let me just give you a slightly more concrete version of this. If there's only one self-dual and one anti-self-dual tensor field, then they combine into a single tensor field, just like in the Green-Schwarz mechanism in 10 dimensions. So in that case, our omega, our inner product matrix, is a 1-1 form, is a 1-1 inner product, and we know that the general form of that is going to be this 0-1-1-0 matrix. And so if one of the anomaly conditions will tell us that A squared is equal to 8, which we'll see in a minute. So we can choose A to take this form -2, this vector, and we can parameterize B as alpha, alpha tilde. And then when we take this product here, the anomaly cancellation condition becomes that I8 really does factorize, because this is an off-diagonal. We just multiply x1 by x2, where now we have a trace r squared minus alpha trace f squared and a trace r squared minus alpha tilde trace f squared. This is the form in which this appears most commonly in the literature, because most of the work has been done on anomaly canceling theories with t equals 1. This is the more general form. So by itself, these anomaly cancellation conditions are not quite enough to constrain the set of theories to some finite set, even at t equals 1. As I'll talk about next time, for instance, Schwarz, many years ago, wrote down an infinite family of theories which satisfy anomaly cancellation according to these conditions with t equals 1. If, however, we put in a further constraint, which is that the kinetic terms are physical, And it was shown by Senyotti that the kinetic terms for the gauge fields, trace F squared, are related by supersymmetry to the couplings between the B field and the trace F squared, right? So there's a BF squared vertex. And that's related by supersymmetry, since the B field is related to this scalar, to something with this J vector in it. And it turns out that's J dotted into this little B vector. This controls the kinetic term. And that has to have the correct sign for us to have a well-behaved physical theory. So with the further constraint that this sign is positive, the combination of the anomaly conditions and this positive definite constraint is enough to give us a very strong constraint on the set of allowed six-dimensional theories. So I'm going to stop there for today. Next time I'll start by briefly showing you how to constrain the set of theories, and then I'll start going through these different constructions, the intersecting brane models, the heterotic or magnetized brane models, and then the F theory down to 6 dimensions. Happy to take any questions as people go out. Yeah, so I'll start with this again tomorrow.